Hello, everyone. My name is Nicholas Muscolino, and I'm a sophomore majoring in computer science in the Randall Research Scholars Program. This semester, I've been conducting research with Dr. Travis Atkinson in the Computer Science Department as a part of the Digital Forensics and Control Systems Security Lab. One of the biggest challenges space scientists research face is the observation and characterization of the Earth's ionosphere. This project, the Personal Space Weather Station software development, focuses on creating a device to do just that. But it's important to understand first what the ionosphere is and why it's important. The ionosphere is a region of the Earth's atmosphere located 50 to 300 miles above the Earth's surface. It gets its name from the high concentration of charged particles it possesses due to bombardment by radiation from the sun. Another key property is known as ionospheric variability. This refers to the constant changing of the Earth's ionosphere over the course of time due to a number of factors. As I mentioned before, the time of day can have a severe effect on this, particularly due to the large amount of radiation it receives. The tilt of the Earth's axis and the 11-year solar cycle during which the sun's magnetic field flips also can have dramatic effects. This variability is significant because it can have effects on radio waves necessary for communication and navigation. It can dampen, bend, or deflect these waves, which can result in interference or a complete and total loss of communication. As I mentioned, it's notoriously difficult to observe, which brings me to the importance of this project. The Personal Space Weather Station, or PSWS, is a project being developed under the Ham Radio Science Citizen Investigation Collective and funded by the National Science Foundation. The project is being led by the University of Scranton with a number of collaborators, in addition to the University of Alabama. The PSWS itself is a ground-based multi-instrument device that's being used to observe the ionosphere and other effects of space weather. It'll be able to function both as an individual unit as well as part of a larger network. The word personal in its name refers to the fact that it's available to both professional researchers and ham radio operators. These are individuals with a passion for amateur radio communication. Professional researchers will use the device to improve their understanding of the relationship between the neutral atmosphere and the Earth's ionosphere, as well as improve models used to predict how the ionosphere will change. Ham radio operators, on the other hand, will use the device to gather data on how their signal propagates in response to ionospheric variability, as well as generally inform themselves about the effects of space weather. The device itself consists of two primary components known as the local control unit and the central control system, which I will get to shortly. The local control unit refers to the physical PSWS system and its software. Two versions of this software-defined radio, or SDR, are being developed. The first is known as the low-cost version. This will cost around $100, but will lack the storage capacity and precision of the other version. The second version is known as the Tangerine SDR. It will cost around $1,000 and will have access to external storage and several instruments that will help improve its precision. Both variants have access to a number of methods of data collection and uploading to the central control. The first method is a snapshotter. This is useful in instances of low internet because it will upload small 1-second snapshots of data rather than the large amount of data collected and uploaded by the second method, the ring buffer. The ring buffer collects and stores up to 24 hours of data that can be uploaded to central control upon request. The third method, known as the fire hose, will collect and upload, or will continuously upload a stream of data to a local supercomputer, which can then be uploaded to central control if desired. The fourth method is known as propagation monitoring, and unlike the others, does not collect data to be uploaded to central control. This is a technique used by ham radio operators to gather data on how their signal propagates in response to the ionosphere changing. The other component, the central control system, serves as the basis for the PSWS network and ties the individual units together. This is how users will interact with the This is how users will interact with the overall network by allowing them to upload their data here. This is also the current focus of our project. It's being created using something called Django. Django is a Python-based web framework that alleviates a lot of the difficulties of standard web development by providing useful shortcuts to help write code faster. Django allows several apps to be created within a project. So we currently have two main apps, an accounts app that allows users to create an account and interact with the network as a whole. My role in the project is creating the second app, known as the Stations app. This will allow users to create, as its name implies, it will allow users to create stations that will be linked to their account via a token generated upon creation. Once it's completed, this app will allow users to, this will allow users to view a list of their stations and the observations made by their stations. An important facet of the central control system is the database control system. This organizes the data users upload into so it can be analyzed later. Some examples of databases will collect information on users, their instruments, and the observations made by their instruments. As an example, the observations database will contain fields such as the data type, the center frequency of data collected, and the type of instrument used to collect the data. Now, as a quick recap, users will collect data using their local PSWS units. The data they collect can then be uploaded via the internet to the PSWS network. It will be gathered by the central control system and processed by the central database system to be prepared for analysis. This project's still in its early phases, so there isn't much data being collected. But there are prototypes of the Tangerine SDR that were used to collect the data you see here. The center frequency can be faintly seen here in the top graph. This is the data that this data was collected over the course of one night when one would expect the ionosphere to be relatively quiet and unchanging due to the lack of radiation and exposure to the sun. However, there are clearly some breaks in the graph that are shown. These breaks are due to a phenomenon known as traveling ionospheric disturbances. These are disruptions in the electron density of the Earth's ionosphere that can propagate for exceptionally long distances. As a result, changes in the ionosphere from extremely far away can cause breaks in the graph of data collected in another location during nighttime. Moving forward, this project has several short-term goals that would involve the continuing development of the central control and database systems. Our next steps will be to develop a heartbeat monitoring system, which will allow the central control to determine which stations are online. In the long term, we hope to have the individual units ready for distribution and the network up and running in time for a solar eclipse that will be occurring in 2024. Hundreds of systems will be concentrated in the areas of partially total eclipse, where the moon's shadow covers the Earth's surface. This will allow for high precision data to be gathered on ionospheric deflection of radio waves that will be essential for the development of models used to predict its changes in the future. Thank you all for your time and attention. With that, are there any questions?
Yeah, Nicholas, you did a great job of explaining the personal space weather station. How does the PSWS differ from existing methods of ionospheric observation?
That's a great question. One of the methods that's in use now is a machine known as an ionizon. This is a machine it's a very large and expensive machine that emits a pulse vertically towards the ionosphere and then gathers data based on the waves that are deflected back towards it. So similar to our PSWS in that respect. However, the PSWS will be much more affordable and available will be much more available. There are very few ionizons in use. So the availability of the PSWS is the real advantage here. It's going to be able to gather much higher precision data due to the large sample size of the data being collected.
What are the hardware components of the PSWS?
So both the versions of the PSWS are fitted with an antenna that will gather the data. Some will be able to be fitted with 2 antennas, and each of them will be hooked up to will contain a data engine that's used to collect the data from the antenna once it's gathered. From there, each will be able to connect with a single board computer, such as a Raspberry Pi or an Odroid N2. And they'll also each have some kind of storage capability. In the low-cost version, this is a built-in micro SD card And the high precision version, this is an external hard drive. And the high precision version will also be fitted with a highly accurate clock known as a GNSS discipline oscillator, as well as other instruments like a ground magnetometer that will help increase its precision.
What other advancements or discoveries could be made by observing the ionosphere with the PSWS?
That's a good question. So there's another discipline of astronomy known as radio astronomy. And unlike the standard visible light astronomy that many people are familiar with, this focuses on properties that we can't see through standard telescopes. There are special radio telescopes that are used to observe radio waves that are emitted by various celestial bodies. But these radio waves are bent by the ionosphere and deflected, just like waves we use for communication and navigation. So sort of touching back to what I was talking about earlier, this will, by understanding how the ionosphere changes and being able to predict it, we'll be able to account for these inaccuracies in the waves emitted, which can sometimes vary by up to an entire order of magnitude as a result of ionospheric interference. So developing these high precision models will be essential to helping with radio astronomy as well.
Nicholas, great job in your presentation and on this fascinating research, and a special thanks to Dr. Atkinson for attending your session today and sponsoring this research. Thank you both very much.